My name is Mark Evenson, and I will speak about Reflections on the Future History of Arming Bears, a presentation in the Online Lisp Meeting series. This is not actually about arming bears, but about Arm Bear Common Lisp, which is a conforming ANSI implementation of Common Lisp that runs upon the Java virtual machine. Arm Bear has a long history, reaching back to the 90s, so I will start with some remarks about what I know about that and what I sort of found in the community that when I started working on it in 2005. Then I will speak about the two major releases over the last 6 months, ABCL 1.6 and ABCL 1.7. And I will use that as a springboard to talk about the features of what would be present in an ABCL 2 scheduled for release in September. Let us begin. So, who was I in 2005? Well, a much younger man and a much less experienced programmer. Uh, I had actually been used eLisp since 1987 because Emacs has been my primary editor, but I have to say that I really didn't appreciate Lisp for all its wonder and beauty as I currently do. I was working as a commercial Java programmer and was sort of at my wits' end. It was very bored hooking up GUIs and all the kind of standard stuff one did in Java. I encountered Peter Seibel's text, Practical Common Lisp, started to get a little bit of the spirit of what was sort of then called the Lisp Renaissance in 2005, as a new generation of people were starting to pick up Common Lisp. Uh, in 2020, when am I? Well, I'm perhaps armed with enough lambdas to be dangerous, but I still know that I know very little compared to what I should. So some remarks on ARM Bear Common Lisp as I found it. So ARM Bear Common Lisp started as an extension language for an editor, J. It was written in Java. It was written, as far as I know, entirely by Peter Graves. He had basically scratched the itch to make a customizable Emacs-like editor entirely in Java. He knew Common Lisp, and so he made his extension language like Common Lisp, and then eventually he filled it in. Um, by 2005, uh, he was sort of tired of maintaining J and ABCL underneath it, and he asked around for people who would take it up. He wanted to work on XCL, which was a C++ implementation of Common Lisp that initially shared a fair amount of the ARM Bear Common Lisp code. Another individual who was pretty active is Andreas Simon, who also an individual I haven't met, and they had actually succeeded in creating what was pretty close to a conforming ANSI implementation. Notably missing was the long form of class method combination and a manual, which is a requirement for a conforming implementation to have a manual that states compliance or non-conformance to the standard, and then your conforming standard. So there was essentially four individuals who, out of the mailing list, contributed patches and worked on online. Eric Hulsmann, Ville Voltan, I hope I pronounced that right, Alessio Stala, and myself. Later on, we got substantial help by Rudolf Schlatt, who actually coded a MOP implementation. So initially, Eric did all the heavy lifting. He actually knew quite a bit more about compilers and computer science in general than I did, and really fixed the kind of like major gaps that were present in ABCL. Uh, about 2007, 2008, we actually started to package ABCL as a separate implementation from J. And the J editor actually was maintained by another group community of people and users and so forth, and we would provide them releases. I don't think there's been an release of J since 2010, so that's pretty dormant. But that was the initial way it went. Um, and when I say it was close in 2005, it was close for suitable values of close. And it wasn't until 2011 that we were able to really declare this as an ANSI conforming implementation at Amsterdam in ELS 2011. So that's remarks on what ABCL sort of was and what I found. And let's talk about the last 6 months. So, well, to get up to there, for the last 10 years, I don't know, maybe 2011, 2012, I took over more as the release manager of ARM Common Lisp. Eric's interests sort of drifted to other things, and actually, so I essentially became the de facto maintainer of ABCL, doing the release management. And but I always consider my position as really managing a community of users rather than really providing guidance. Although over time I've sort of, I guess I have guided it. Okay, so ABCL 160. So this was released in December of 2019. And the major problem here that we overcome was that ABCL uh, no longer worked on contemporary job implementations. Uh, the Oracle had begun in 2017 to get very aggressive in the release of JVMs. They decided that they would release a new version of the JVM, the Java Virtual Machine, every 6 months. And they announced that the OpenJDK 8 platform was essentially end of life, and OpenJDK 11 would be the new current long-term release. At this point, most Linux distributions no longer ship with OpenJDK 8. And as of December 2019, there really wasn't even a way to run ABCL on OpenJDK 11. OpenJDK 8 was the last release that it would work on. The major problem here is that Oracle had begun a process of introducing what they call a module system. A module is an abstraction of a collection of packages and an abstraction for sort of isolating or encapsulating these modules away from each other. Actually, for OpenJDK 9 and 10, there were major restrictions on what code could call another code from modules. And this actually provided or caused a lot of problems to get ABCL running on it. When I initially looked at it, it was a pretty immense task. But luckily, or whatever, by waiting, we actually gained because a lot of other users of the Java virtual machine found that these to be burdensome as well. So it really wasn't until the long-term release, the OpenJDK 11, that we were really able to port ourselves to there. The major thing there is that the way that ABCL loads stuff no longer existed. They had moved to a way in which the jar archives that had formed in from OpenJDK 8, the basis of the implementation were no longer the way that the system packages were packaged, and therefore when ABCL booted, it couldn't find the resources that it needed. So I was able to implement a new strategy to find things for CL load that worked with OpenJDK 11, and these were actually surprisingly few once I was able to figure out what we needed and what we didn't need. And then we have currently retained the old strategy for jar files running in OpenJDK 6, 7, and 8, backwards compatibility. There are actually few statistics about which communities are using it, but I do know that since Java is now sort of a legacy operations, that I have encountered working commercially, you know, implement shops that basically can't move forward for this reason or that. And in general, Oracle has, well, Now they're trying to move things forward faster because the JVM platform was perceived as kind of moribund. So that was ABCL 1.6. That was done in December. And of course, there were a whole bunch of bug fixes and stuff like that. But the major achievement here was being able to actually say we had a future. Uh, ABCL 170 is, well, it started from my desire to run Righetti's quantum virtual machine on ABCL. And because when you're doing quantum computation or simulation of quantum computation on classical machines, you tend to you need very large matrices and so forth. Uh, they need to be able to access through stuff like static vectors and magic L libraries like that. They need to be able to access memory that is not garbage collected, so that you could allocate memory within your common Lisp implementation and then use like LPAC libraries and so forth to manipulate it on it. So a little known feature of ABCL is that actually we are pretty, we're certainly able to basically access native code, or code that could be shared objects that could be opened by DL Open or its abstractions. Uh, and that was predominantly work with from Luis Oliveira. I hope you pronounce his name right, and Cyrus Harmon. Um, but because of the way the JVM is set up, because it has to be able to garbage collect, right? ARM-Bear Common Lisp doesn't have its own garbage collector. It relies on the JVM to do its garbage collection, which is both a strength and a weakness. It's a strength because there's a lot of innovation that goes on in the JVM, because it's the premier virtual machine that a lot of software runs on, and so a lot of research is done on how to make general purpose garbage collectors, or different ones. So you can actually sort of plug different garbage collectors in depending on the JVM version you're running and what is implemented in there. So with 1.7, I've been able to extend the implementation's creations of arrays specialized on commonly used byte types to use memory allocated outside of the JVM's heap. To do this, I've extended the ANSI make array call with an additional keyword to take a specialized Java object called an NIO buffer. Comes from a package called java.nio.buffer, which has a generic contracts for byte buffers. And this is interesting not just because then you can malloc memory that's not under the JVM's garbage collection, but you can actually use that to actually memmap or memory map files into the memory. So I was able to implement that pretty quickly. It involved a large overhaul of the byte of our arrays, specialized on bytes. And I was able to get to the point that CFFI sys now contains an implementation of make shareable vector. And to give you a little flavor and to get a little code into this otherwise dry presentation, here's the actual code from CFFI at this point to make a shareable vector. Here's some setting up, some signaling if we're not being passed a proper type. And here is where we actually uh, uh, this call here, the JSS new here, actually creates memory from malloc. And then here we create this NIO byte buffer abstraction. And then here is the make array, which was a standard CL make array with this additional parameter to specify the byte buffer. This nonsense here is my current hack, because once this array is created, there's actually no way to get back to this reference here, which is the heap pointer to the malloc memory. So I hack around that by keeping a hash table present of the allocated static vector to the actual pointer, and that's useful later for cleaning up and stuff. And that is the major change that happened in 170. So, what is ABCL2? What could it be? Well, first we have to talk about what ABCL1 is. Well, in my opinion, my humble opinion, it's an amazing piece of code that really runs in more places you would think. So, in addition to the platform compatibility on the large number of implementations, so what has recently happened because Oracle is fairly burdensome in their licensing requirements, a lot of big vendors who depend on Java technology have actually forked the implementation and started to doing their own implementation. So there's several JVM implementations on big name companies in Silicon Valley. And I think Baidu in China has their own implementation and so forth and so on. So we actually run in a lot of more places than the OpenJDK, but because we are a free open source implementation, I basically have steered it to, well, if it runs on the OpenJDK, which has source code, which anyone can build and is unencumbered, and there's no licensing restrictions, that's where we're going to run. But there actually have been successfully getting the interpreter running on the, say, the .NET CLR runtime. Douglas Miles has done that. Of course, there's not a compiler, and therefore it's dreadfully slow, but that's where it's going. But overall, ABCL is slow. It's not just slow because it's Java, although that's part of it. It's slow because its compiler targets old bytecode, Java 5 bytecode, even though we no longer support running on the platform. Current JVMs, because of this backwards compatibility strategy, reach back to it and work. But ABCL is slow to start up because of the JVM startup times, although that's gotten a little better. Uh, it's slow to compile, and it's slow to load those compiled representation. But once it gets going, um, it's actually quite an interesting platform for a lot of for large memory applications because of the research that's gone on into the JVM and the work and the countless engineering. Uh, this it can actually run on terabytes of memory. And garbage collectors exist now which can provide reasonable garbage collection strategies upon them. So, an interesting thing, but ABCL is slow. So, a predominant thing for ABCL2 would be to figure out how to speed up the implementation. So, given that so the current plan for ABCL2 would be to drop support for OpenJDK 6 and 7, target OpenJDK 8. Even though that is end of life by Oracle, there's still a lot of shops that use it, and it is a baseline. And in fact, most people don't use the new features in the new OpenJDKs. Uh, anyways, so what can't we actually do with OpenJDK 6 and 7? Well, it wasn't really until OpenJDK 8 that there was support in the runtime for atomic compare and swap operations. This combined with the story about how we can now allocate memory outside of the JVM on the system heap, not the system heap, but the process heap, would sort of complete the kind of story for the kind of things you'd want to run on those exotic architectures with terabytes of memories and gobs of processors and threads of execution. Because yeah, you're just not going to be able to do parallel computation without some support for threads accessing the same memory, or you would be substantially limited in what you could do. So, in addition to what has happened under the hood with each JDK release, is that the actual JVM bytecode has been augmented and changed. The biggest thing that would give a win for ABCL2 or is present in OpenJDK 8 is the so-called JSR 292, which is a Java extension process by which it was reviewed in the community, which added substantial support for dynamically typed languages. And what's happened here is that within the JVM, there is now an invoke dynamic instruction, where the call site that you're invoking is now has a sort of a handle abstraction, so it has an indirection, but that indirection allows it to be efficiently swapped. Uh, so other languages that use the JVM, say Ruby and so forth, have you. There's a JRuby, which is a Java implementation Ruby that runs on the JVM. They've utilized this for the kind of dynamic typing and the dynamic relationship of the code that constitutes Common Lisp. It would be immensely beneficial. Uh, because it should allow the JVM then to optimize its just-in-time compilations for those call sites. So, in summary, what are our goals for ABCL2? Well, they would be speed, would be number one. Startup, compiling, loading things. So, to do this, I'd like to basically create a second compiler targeting the OpenJDK 8 bytecode implementation that would be reentrant and use these dynamic method sites in the JSR 292 to make the kind of code that one uses to implement Common Lisp much more amendable to optimizations by the JVM and also probably for the garbage collector. That's largely suppositional rather than empirical from the research that I've done. And then we can use the APIs because we will declare that the ABC2 runs on OpenJDK 8 and upwards. We're able to use APIs available on that JDK, such as this atomic compare and swap operations. From my reading right now and from my canvassing of what people have requested for ABCL, that's the only one. But there are some other interesting things present which might be of use. But the ability to use these terabyte heaps with massively parallel computation is really kind of where I'm going with ABCL2. One might argue that at that point, if you're going to run those computations, starting them up isn't really that important. But still, because we're Lispers, we would like our implementation to start and not curse the compiler or so forth and so on. So that's that. So to talk a little bit about a strategy here for the ABCL2 compiler, I have to talk a little bit about what the ABCL1 compiler does and what it is. So what does the ABCL compiler do? So it takes Lisp code and it creates a zip archive which has a set of Lisp forms to be evaluated. Well, it consists of two things. It contains a loader segment, which is a textual Lisp form, which actually tells the loader how to load the rest of the fossil. So that's evaled by the interpreter, and each component it does various things to load the artifact. So going into more detail about this load process. So our facets are addressed by path names. These are used to open a stream of bytes from its CL true name. And the resource will contain one or more top-level forms or be a zip archive. That one or more top-level forms is a special case in which we're loading system code. So we'll ignore that for a second and just talk about the standard case when it's a zip archive. In the zip archive, it opens it up and it finds this loader file. And then it reads and evaluates these forms. These forms are set queues to mostly set queues to set source excuse me, source locations in the FASL, and then actual calls to a function called system get FASL function, which actually loads the classes emitted by the Java compiler. And to load those classes, there's essentially one class for each top-level form that occurs in the Lisp source unit. Those are compiled into a Java class, which basically encapsulates everything in that top-level form. That thunks down to an array of primitive bytes, which is then loaded from memory into the archives. An interesting thing is that our compiler actually emits JVM 5 bytecode. That's how old it is and how much it hasn't been worked upon. And those continue to work in the newer, up to OpenJDK 14, which is where we're currently in the 6 month cadence of JVM releases. So that's our current strategy, and that has a bunch of ramifications that suggest some strategies to increase speed in this actual loading. So the first thing is, uh, because we have a zip archive that's the facile, every element of that facile has to be accessed by the zip decompression scheme, I guess you'd call it. Uh, but there's and that what that means is that the initial loader is loaded, the forms are processed, and for every form, that's going to reference an additional path name in the archive, which is later, as it were. But the implementation then essentially has to seek back to zero, rerun the zip archive location algorithm, and then locate those bytes, bring those bytes into memory from the compressed representation, and then pass it to Java a JVM called define class. So that means that for long Lisp source units, the time is going to then grow as the number of actual top level forms. So, in some sense, you could perhaps speed up the implementation to some level by writing only one form in a file, which would totally be practical for easy Lisp. So, an easy way to win that would be to actually make a single synthetic Java class and containing all those methods. And that should be pretty easy to do with a compiler. I believe that the compiler is in its current state because it was essentially it wasn't Peter Graves' interest to make a fast Common Lisp implementation. It was in his interest to extend his editor, and the compilation strategy and all that stuff. It was added on incrementally as it could best be done. The second thing that we can do to increase the speed is that because we use this Java 5 bytecode representation in the artifacts that we emit for our faciles, we actually are using a very old version of the layout of the Java file. So when the JVM encounters code that it's going to run, the code has to follow certain validation procedures, and there's essentially two strategies in the Java language specification for what this is. Excuse me, the Java virtual machine specification. That is type checking and type inference. So and as you can see here, and this is a quotation from the Oracle docs for the Java 8 VM specification, uh, the type inference doesn't have to be done on so-called Java card and Java ME. These are sort of light, very memory constrained JVMs that run in sort of feature phones and stuff from the early 2000s. That's the source of Sun's claim and Oracle's claim that Java runs on a billion devices, because there's actually a fair amount of sort of embedded Java in a lot of early feature phones and so forth. And that's because the type inference is a much more expensive operation in terms of the things you have to do. Um, type, but therefore, because you have to specify a lot more information, and on load, there's a lot more information present to the JVM. The current JVM implementations with the type inference can do a much better job of validating that the class is able to load, right? More stringent checks that it won't blow up the JVM, and it is also able to optimize the just-in-time compiler much more. So by adding this additional information to the bytecode representation that we emit for our compiled forms, we should make the loading occur faster and more efficient in terms of the execution on the JVM. The third thing we can do in the ABCL compiler is that the ABCL1 compiler is not reentrant. It is as I said, a construction, a labor of love, of progressing, rather than written for maintainability, as it were. And it actually uses a whole lot of state stored in lexical and dynamic scope as it goes through. So through proper uses of lets and so forth, one could, uh, there's no reason that the compiler couldn't be made reentrant, and therefore more than one thread at a time could be loading. You could take advantage of the parallelism to have more than one thread actually loading the code. Now, there are subtleties in injecting these things into the Lisp image at the same time, um, in terms of references and so forth, but at a minimum naive strategy, you could certainly do a lot of the work of actually bringing them into, say, a separate. So Java has this idea of a nested class loader, and so you could bring it into like a subordinate class loader to the current class loader, and then perform checks. So you should at least be able to get some amount of efficiency by making a reentrant. And also by going through and doing all that stuff, it would make it much more, by making reentry and cleaning up the variables, so you could actually stop it and checkpoint the compiler in a much more amendable manner. It'll make working on it and extending it easier. So I would like to keep the current compiler, but build her younger sister. And to do this, I'm salivating at much of the pioneering work that Robert Strand and his merry crew of pirates have done in Cleaver. Really great stuff that I see no reason that can't be used more or less directly. And then we should be able to, as I spoke earlier about, expose the dynamic method dispatch. And that would be the major goals for what ABCL2 would contain. So, a roadmap to ABCL2, I've set a date in the sand sometime back for September of this year. It's June, it's the middle of June, and this is probably way too ambitious to say that a new compiler, fully formed, would be present by September, if it is just I that will be creating it. So, my best current guess of what I can do by September is I can certainly implement these atomic compare and swap operations. And again, that would be enough reason to why you would want to call it ABCL2 instead of ABCL1, because the JVM primitives are not present in anything other than OpenJDK8. So that means we're going to move the platform forward to OpenJDK8 and drop the other two. And then the compiler, we could certainly fork the current compiler, leave it as is in some extent, and let it run. And rewrite it to be a second version to be reentrant and to use the abstractions present in Sickle and Cleaver. And once that's done, and therefore it's more amendable to testing and instrumentation and actually refactoring, as it were, it should be pretty easy to write this type verification bytecode to speed up the process of loading and to allow the JIT in the JVM to do it. And the next step would be is to look at what Invoke Dynamic could do for the implementation, to start to work on that. So that would be ABCL2. So in conclusion, I'd like to thank you for your attention to this future history of the ARM Bare Common Lisp implementation. I'd like to jangle the proverbial cup to note that there is an ongoing ABCL appreciation campaign being run by the Common Lisp Foundation. And if you feel like you're able in these troubled times to provide some modicum of financial support, I and hopefully other users of ARM Bare Common Lisp would definitely appreciate it. Thank you for your attention, and goodbye.